And this gives us a very typical linear programming format. So on the other hand, we also have links, which are sometimes arc edges or branches. I prefer using the links format unless someone really uses something else, but I think a link is a more neutral way. An arc sounds like it's rounded, and an edge sounds like it's inside of things, which is not really true, and a link really, it basically links to nodes, that's really what it does. So between the two nodes, they can represent growth, but also air lanes. So if we're just looking at an air traffic management network, then we have the air networks going from one waypoint to waypoint. These are basically links, but also pipes, but also things like computer network cables, lots of things like that. They can be directed or undirected, so to mean they can be, you can only allow flow in a single direction, or you can actually allow flow in both directions, in which case most of you will actually use two links, in one direction or the other direction. And often also what you'll see is that you'll have a capacity limit on the flow that will go through that link, so which of course adds a constraint. Sometimes you also see that the nodes have a capacity limit, but this is but of course, in a traffic network, if you have a node representing a sector, then of course you can have a sector limit on how many aircraft can be there at the same time. So then we have basically a path, which is basically a route which connects through the node from one node to another node. So we have the path from O to T, which goes through a number of nodes. So that's a path. We can have multiple paths. If two nodes are connected, so if we have a connected network, that means that a path exists between two nodes. If it's not, then there's no path there. And if it's a fully connected network, then actually each node combination actually has a path running between them. Yep, so these are basic, let's say, elements of a network. So we'll go through three different network models. Maybe the first one is maybe the most used, and probably for most people the most important. It's the shortest path algorithm. Anyone can name an example of when we find the shortest path algorithm? What would use the shortest path algorithm? Google Maps, yeah. Well, your sat nav. So indeed, Google Maps, they use the shortest path algorithm. Not quite the one I showed you, slightly more advanced ones. Split it up. But yeah, so satellite navigation, yeah, that's a very important application of the shortest path algorithm. Spanning trees, which is in itself not that useful, but it does give us fundamental insights in how to solve a network problem. And we'll talk about maximum flow, and what we talked about here was actually also the minimum cost flow, which will also which isn't on the slide, but we'll also talk about the minimum cost flow. So we'll start off with the shortest path algorithm. So this is the second example, which is also in the book. It's the Sirvada Park example. And what we basically here is we have an origin with O, and we have a destination with T, and we have a number of road networks in between, and you'll probably notice that the length of the link actually has nothing to do with the actual distances. So this is just a model representation and in no way geographically accurate. So it's not a map. You see there's basically a bunch of nodes and distances, and what we want to do is we want to find the shortest distance going from A to T. So how do we do that? Well, you might think, oh, let's try all the different possibilities, but that would be well, quite a long way to do that. Well, let's start off with, there's basically two ways to solve this. First of all, let's do the LP formulation. So how can we make a linear programming model to give us the shortest path? This is not normally the algorithm, the Dyson algorithm, which we'll discuss later, is more efficient, but still, if you have special constraints, you have special requirements, special objectives, then you might still need to use an LP formulation. So how does that look like? Let's go through the math a bit. Basically, we have I, J, and K, which basically stand for nodes. So we have a set of nodes. L is basically the set of links. N is the set of nodes containing all the nodes. Basically, one is the start, which is O in this case, and one is the end, and the rest is transit. And basically, our objective is to minimize the length of the path times xij. Basically, is a binary representing if a path is used or not in the shortest path. So it's either 0 or 1. In this case, again, because it's a lot like a assignment problem, We don't need to define it as binary because of the constraints. It will actually always be 0 or 1 because we're looking for a cornerstone solution. But yeah, so it's basically a binary variable. So we want to minimize the total length of the path, so the length of each path times if we choose or not. Well, again, the sum of the flows for each transit node must be equal to 0, which is a fundamental network characteristic. So flows to the start node must be 1, and start through the end node must be -1. And basically we have, that's basically what the formula says. So the top one basically is our objective. The second row is basically the incoming minus the outgoing nodes. So the incoming links minus the outgoing nodes for each, the incoming link minus the outgoing link for each node must add up to 0 for each node, with the exception for the start node, at which it must be 1, and the end node, at which it must be -1. So, well, for this we can just create a simple LP model. Some of you might also then decide to use an LP solve. So if you want to solve this using an LP solve, I'll show you the next slide. But if we actually look at this model, how many constraints do we actually need if we want to solve a model like this? I'm going to go moving one slide ahead. So in fact, which spot we're going to use, it's still the same as this code. So how many constraints would we need to actually, if we wanted to model this with an LP as an linear programming problem?
The session does not exist.
Oh, that's a good one. Let's solve that. So why should they see the answer? So actually, I'll go with like that. Should work. I think started this one minute ago. Okay. I think it should be working now. Let's try again. No. Is it working? Yes. Okay. Okay. You're able to see the question now? Again, it's not showing me the. Yeah, start the timer. So 64% of you, 2/3 of you got the correct answer. So we need one constraint per node. There are 7 nodes, so hence we have 7 constraints. So we don't need to constrain the links. So we don't need to put any passive constraint on the links because we're just dealing with a flow of 1. So we just need a constraint on each of the nodes. Okay, good. So how many variables would we need for the LP formulation? 6, 7, 8, or 12. Yeah, very good. 88% of you got that right. Indeed, so it just counts the amount of links. So each link is a variable. It is used or not by the path, and that's it. So there are 12 links in this case. So we have 12 variables. So we have 7 constraints, 12 variables. So it's not a very big model. Actually, I'll just show you. I think in the next slide we have it here. So the top one is basically the tableau. I actually used Excel to create this. So the top one is basically the tableau. Right here, we basically have our variables, all 12 of them. Here we basically have our constraints. So we see our origin, basically we have from O to A, O to B, O to C, which have a +1 coefficient in O, and some of that has to be 1. For example, for A, we have a OA coming in here, AB leaving there, they have to be added to 0. And of course, at the end, then we have the final node T, which basically has DT and ET going into it and nothing going out of it, and those should add up to -1. So if you then put it into an LP format, this is something you just copy paste into LP solve, first run, and give you the answer, then it basically looks like this. So it's on and here basically, so you see the same thing, but then in a purely LP text format, so you just copy paste. Yeah? And here also you see nice and deep, and here you see basically the objective is basically the multiple of the distance times the variable. And that's some of that basically is our objective. So, well, this works for smaller models. For bigger models, there's a much more efficient way. And that's Dijk's algorithm. Dijk was actually a Dutch mathematician, I think from the University of Amsterdam, and he came up with this way of actually finding the shortest path much more efficiently. So the LP model, of course, tries to solve everything at the same time, while this is a clearly orderly model, which goes through basically the steps and through the network until it finds the shortest path. The book actually has a slightly different method to do it, I would definitely say use this one. So the advantage of the one in the method is that you don't have to override the node, but it requires a lot more lookups, which makes it a lot less computationally efficient. So Dijk's algorithm is far better, and I don't understand why the book is point to it, which is one of the things in the book I disagree with. So I'll go through Dijk's algorithm, but they look very similar, but the difference is in lookup. So how does it work? Well, we start off with our origin. So we start looking from there, okay, what points is our origin connected to? So we see on the right here, actually we have here a list with all the links, and here actually we have a table with all the nodes. If you would program it, this is actually what you would use. So you would have one array, basically one matrix with your links, and one matrix with your nodes. And this basically being input, and this one being output. So now O, basically we say, okay, this is now a nearest node, and now for O, we look at all the different nodes connected to it, and we simply write down in those nodes what the distance is to those nodes. So we see the distance to A is 2, to B is 5, to O is 4. You can see here, we write this down. A is connected from O by a distance of 2, B is connected from O by a distance of 5, and C is connected from O by a distance of 4. So now it's quite simple. So what do we do next? Well, what we now do is we look at the nearest connected unsolved node, and we start there again. So in this case, A is 2, B is 5, C is 4. So A is actually the nearest unsolved node. So now basically we move to A, mark that as the nearest node, and then we start, okay, how is that connected to? Well, A is connected to B and D, B with a distance of 2 and D with a distance of 7. Which basically makes the distance to B a total of 4 instead of 5, which it was from O. So we actually find the shortest path to B. So actually what we do here is that we actually now we cross this through. B is a distance of 4 now from A, and D is a distance of 9 through A. So we now write down the total distance. So A is 2 plus 7, so that's 9. So D is the total distance of 9. Yeah. Now we look again. Now, what is the nearest unsolved node? So A has already been solved. So also when we calculate the distance, we ignore the already solved nodes, which are marked with the nearest here. And we look, okay, we have B and C, basically. Okay, well, where shall we start with? Well, I think in this case, we'll start with C. So we now have B and C at the same distance. So now we'll start looking at C. Well, from C, we can go to B or E. And of course, O is already solved. So we're going to ignore that one. The distance is always going to be longer. So a very important premise of Dijk's algorithm is that you have to have 0 positive distances, you're not allowed to have negative distances. Well, that seems to make a lot of sense, but if we actually apply, we can also apply Dijk's algorithm as a non-math-like. So if you're talking about interprogramming, you're talking about branch it down, you can actually also apply to solution space, then you can actually have negative distances. So, but in this case, a very important factor is that the distance has to be positive. So if you then look, then B, well, it's actually is 5 away. So that's actually longer than the path through A, so we'll ignore that one. And E, we didn't have any distance to it, so E is now actually a total distance of 8 from C. So it's a distance of 4 from C, but the previous in the path is C. Now, well, then we have actually the next is B, which is a distance of 4, total distance of 4. So we look at B. Well, B is connected to E and D. Well, if we look at D, then that total distance is 8. So that's actually also shorter than the 9 it was through A. So actually we replace that. And actually E is now 7 from B. So we also have a shorter path to E. So we replace that as well. Now, what is now the next unsolved node? So now we have unsolved connected are D and E, 8 and 7. So E is the next, let's say, unsolved node. So we move to E. Well, D is a distance of 1. That's actually the same as what it was. So we'll just leave that unharmed. So that's so that will be 7 plus 1. So that's 8, but it's already 8. So I think in this case we'll ignore the new path. Just take the old one. And actually we now have a path to T, which is 14, which is basically 7 plus 7. Okay, let's put the display controls here in the way. Okay, now the only unsolved node except for T is D. So if we now look at D, then because D is actually closer than T, we still have to look at it. So we might still find a shorter path. If, for example, D would have been a total distance of 15, we could have ignored it because D could never have given us a shorter path than we already have. So it also allows us, if we're looking through a network, to actually, once we found the shortest path, we know that no other path can be shorter at one point, so we can actually also ignore a lot of those. But in this work, we still have to look at it. So D is a distance of 8. Well, D is only connected to T by a distance of 5, which gives us a distance of 13. So indeed, that means that that's actually shorter than the distance we had before. So now actually T is a distance of 13 going through D. Yeah. Actually, if I probably just switch this in. Actually, you can now see the whole table. So, but I have to switch back and forth and I'll do it here. Yeah. So okay, now we basically have this table. So what do we now know what the shortest path is? Well, what we have to do now is start backtracking. So we start looking from T. Well, T is connected from D. T is connected from D. Then we look at D. D is connected from B. B is connected from A. And A is connected from O. And that basically means now that our path is OA, B, D, T. So we've now found our shortest path. And this, and the great thing about Dijkstra is that it scales quite well. So if you use an LP method, then well, you can imagine if you have 10 times the nodes, you have 100 times the links, and it completely explodes. And this one is a lot simpler, it scales a lot better. There's actually, specifically, if you're looking at maps, and there's actually A star, which is like an improvement. And that takes into account the actual physical distances. So on a map, you can calculate, you have your location, you have the final location, so you know the absolute distance. And therefore you can also build in a tendency to go find in that direction. But also you know if a certain point, the absolute distance from a certain point is longer than the path you already solved, you can actually already ignore that. So it's a much smarter way of looking if you actually know absolute distances. So this is a fairly dumb method. We don't look at actual geographical locations, but if you do, there are actually even better methods to use. But Dijkstra is fully applicable and is the most normally used. Any questions about shortest path? So have a look through it. I'll try and make a video of it so you can also look it back and see how it works. And of course, there's also the homework assignment, which helps you understand it. So another typical network problem is the minimum spanning tree. The minimum spanning tree basically means that what we want is a network which connects each node to each other node through a number of links. So through a path. So we want to make sure that each node must be connected to each node through a path, and we want to minimize the total sum of the link cost or the link length. So last week I said MC work was looking at a hyperloop network. And here also, I suggested, well, the best thing to start with is actually a minimum spanning tree. So with the least amount of tubes, you can basically connect everything and then use that as a starting point for your network. So this is one of the applications. Switch back to the bottom right again. Okay. So how do we solve? So well, how many active links do we need actually to create a spanning tree for this network? So we now have the basic set network. So how many links do need to be active to create a minimum spanning tree? So we want to basically connect each node to each other node through only one way. Start the timer. Yep, 80% of you got the correct answer. The answer is 6. And it's actually the number of nodes minus 1. So even if you have a million nodes and it's just 999,999. So we need n minus 1 nodes to connect it. And you'll see later on in this lecture, you'll see that n minus 1 come back. Because it's also actually the amount of basic variables that you need if you want to use a network simplifier, which we'll discuss later on. So the n minus 1 is a very fundamental thing in networks. So, well, if you want to use the algorithm, how do we do that? Well, again, here we can actually start every point we want. In this case, we'll start with the origin. What we do is we look at the nearest unsolved node, which in this case is A. So in this case, actually, we'll look towards A. Now, actually, for our next node, we have to look at the next unconnected one. So we now have in yellow, I indicate the list of nodes which are now available. We basically have B, C, B, and D available. And from here, we connect the closest one, which is B, which is a distance of 2 from A. So the next one we take, in this case, is B. Now, actually, we've also added E and C, D and E in this case, to the network. Now, from the yellow one, so the yet unsolved one, again, we connect the closest one, which we see is C, which is only a distance of 1 from B. Yeah. So if you see, is actually, so if you look here, the nodes we could connect to now are C, which is a distance of 1 from B, E, which is a distance of 3 from B, and D, which is a distance of 4 from B, and C, the closest one, so this is the next one. So we'll take that one. And now actually we have another path towards E, which is a distance of 4. However, if you look at this map, then actually the shortest link now available to us is actually connected to E through B. So that means we connect that one. And now we basically also have a connection of ET. No, that's not connected yet. That's the only link not available yet. But we have ET, which is 1, and we have DE, which is 7. This one is 1. So actually, this is now the available link with the shortest distance. So we now connect this one. And then the only one still available is T. And then if we look here, then basically that's a distance of 5 is actually the closest connection to T. So we take this one, and now we have our minimum spanning tree. So now if you add up all the distances of these links, we actually get the total distance we need to connect this. So what does this mean? Well, the minimum spanning tree in this case, this is about a park example. This is in the book they talk about a phone line. So they want to have these are all points in the park. They need to have a phone connected, and they want to use the minimum amount of wire to connect all the different points towards the network. But also, if you look at a computer network, again, this is the minimum amount of links we require. And of course, this is not looking at capacity. So if you look at capacity, of course, then it becomes a different story. So now we actually have a minimum spanning tree. So how can we actually create a minimum spanning tree with an LP formulation? Well, we have a nice algorithm, but still, there might be a lot of additional constraints. So this is just trying to minimize the total length. But there might be a lot of other additional things we want to do. For example, we want a minimum capacity added to it, or or there are certain links which is rather not used, might be a different cost for different links, and then we can't use the minimum spanning tree. In that case, it's actually interesting to look, okay, how we formulate this as a linear programming problem. So in this case, again, here, I, J, and K are basically the nodes. L is a set of links, N is a set of nodes, and one is start node, one is the end node, and the rest is transit. So similar again to the short path algorithm. Our objective is again to minimize the total length of these paths. That's exactly the same as the shortest path algorithm. And actually, what we see here is, however, our constraint is slightly different. So where in the shortest path algorithm, we needed to have one ingoing coming and one outgoing node. Here, one incoming and one outgoing link. All we need to basically enforce here is that each node is connected by at least one link, right? So we'll minimize the total sum of length of activated links, and each node should be connected by one incoming or outgoing link, and it doesn't really matter which one. So we actually have a bidirectional system. Okay, so who thinks this will work? No one? What could possibly go wrong? So I'll try to show you the way you have to go through, if you want to create your own LP model, how you go through it, and it's really like a trial and error kind of thing. So okay, let's apply this now to our network. So we want to minimize some length of the activated links, and each node should be connected by one incoming or outgoing link. So what is the solution we're getting? This. So indeed, every node is connected, has one link attached to it, and indeed, yeah, so this completely fulfills our LP model, but it's not quite a spanning tree. In this case, actually, what the problem is that I didn't enforce that we need to have n-1 links. So in this case, we only have 4 links, which of course is much nicer because we get a much smaller network. So it's much more small actually, but it's not a minimum spanning tree. So okay, so I need to add something to this model. So I need to make sure that it chooses n-1 links. So okay, let's add that. So the number of links that is activated is basically the number of nodes minus 1. So we have to enforce that. So sum of this has to be n-1. Okay, good. Well, let's see what happens now. Okay. Yeah. Okay, so now basically has 3 links between B and E. Okay, so that wasn't supposed to happen either. Okay, well, that's quite easily solved. So what we do now is that we also add a constraint, in which we say that we can have no more than one per link. So 1 link per node combination. So xij has to be smaller or equal to 1. Okay, added that as well. This basically means that it's more or less it's quasi-binary, I would call it. So it has to be always larger or equal to 0 per definition, unless I say otherwise, and then it's smaller or equal to 1. Okay, and this, well, wow, we have the correct answer. So that was it. So who thinks indeed this is the correct answer? Huh? Probably not. Very good. You're very good at reading me. That can you also read an LP solver. So one of the problems you'll find is that the solver is sometimes more creative than we are, and it finds very creative ways of answering all our constraints without actually meeting up with our expected problem. So yes, it solves it in this problem, but will it solve it in all problems? Well, let's just change the model slightly. Now what we've basically done is that I've changed these values, so OA, AB, and OB are actually 1. Yeah? And now let's run it again. And what do we see happens? Okay. Not quite a minimum spanning tree because, well, the left side and the right side are not connected. Still, however, it answers to all our constraints. So within our model, this is an acceptable answer, but it's definitely not a minimum spanning tree. Now, this is where you'll go, okay, how do I solve this one? And that's the point where, as an engineer, you actually start looking at the books and you start looking up, okay, how actually should I solve this? And then you find a slightly nasty mathematical notation, which we're looking at in one of this, and that's this one. So what does this mean? I guess most of you are also engineers like me, and like, what? yeah, S is absolute value minus 1, and then S is part of V. H, or what is V? So the rest is still the same, so we still have to minimize the sum of activated links. We still have to make sure that n minus 1 links are activated. Actually, the new constraint will actually also already enforce that. And X is, well, 1, 0, 1 binary. But in this case, because we're looking for a corner point solution, we don't need to define a binary because it always has to be 0, 1, 2 to be if it's a corner point solution. The new constraint actually is known as subtour elimination. And so basically what we have to do is we just have to make sure, eliminate all the cases in which it can actually find a subtour. So we have to basically manually, well, semi-manually eradicate all the subtours by adding an extra constraint. So basically that means that not only within a full model, but also in a partial model, if we have a sub-selection of nodes, that we should not have more than the number of nodes within that selection minus 1 links activated within the collection of all subsets. So we have to define, first of all the possible subtours or subsets in which we can have a subtour, and then basically also enforce that n is the number of active links within that subtour is equal to n minus 1. Okay, how do we do this? Well, in this case, so how many unique subtours do you think there are in this model? Just take a guess. It's not a very big model, it's only 7 nodes. I'll just start the timer, so just take a guess. So the answer is not 6, because then you probably calculated it. Correct answer is 20. So there are actually 20 possible subtours. So the thing is how, well, for the subtours, well, we need to have at least 3 nodes to create a subtour. And if we have, in this case, we have 7 and more than 5, we also don't have to look at, because then there would only be 2 left, so then it would already violate one of the other constraints. So we have to look at all the possibilities, in this case, between, let's say, 3 to 5 nodes, right? So in this case, I looked at I basically created an algorithm to actually look through the network and quite a rough method to get all the subtours. And in this case, this is, so how do I do that? So we have to decide on a set of links which create this closed loop. Well, we of course have to eliminate backtracking, so it can go back at least 3 nodes, at most n minus 2 nodes, because otherwise there would not be enough nodes left to have their own subtour. So at most n minus 2 more nodes. And of course then I have to remove all the duplicates, because OAB, ABO, BOA, OBA, BAO, and AOB are actually all the same subtour. So eliminate those as well. So there's probably a faster way to do this, but I'm an engineer, not a mathematician, so I just do it the trial and error way. So this is basically all of them. OAB, OBC, well, have a look at them. So we have 6 with a combination of 3, 6 with a combination of 4, and then we have 8 with a combination of 5. So all these subtours, so these are all the possible subtours, and of course now we need to make sure that within these subtours, so if we have actually 3 of them, so actually it's OABO, so but I've eliminated, so OABO is actually the full subtour, but I've just left out the last one. So in this case we have 3, so in this case for all of these, this should be at most 2 links active between these should have at least at most 4 links active between these and these at most. These 2, these 3, and these 4. Yeah, so for each of these subtours now we need to add a constraint, which basically limits the amount of links between these active. So if we add that, of course, now we do get this network, so we will now be able to enforce it. This is not a very big network. You can imagine if we have at the end I'll show you an example of a very big unconstrained network, which is one of the biggest OR problems ever solved. This runs completely out of hand. And the problem is that most of the time we don't really need these constraints. So again, the original problem, we didn't have a problem with subtours. So they're not very likely to occur. So what you actually see, and there's actually a nice tutorial on the Garobi website where they have a travel salesman problem, where you can actually do this. And what they actually do is they use related constraints. So what they do is they simply solve it like I did before. And it's quite easy to detect also algorithmically if there is indeed a subtour. So you then determine, is there a subtour? And if you find a subtour, then you add a constraint for that subtour and you run it again. And you do that until you've eliminated all the subtours. And that's much more effective than actually adding, like I did, adding all the subtours in one go. Because you have a massive amount of constraints, and most of them will actually never actually do anything. So in this case, again, we use like a trial and error system. So we optimize, check for a subtour, and if we find a subtour, add a constraint, and run it again. And that way, it goes through the model. So, so especially for very large networks, this is far better than trying to figure out all the subgroups. So at the end, I'll show you how bad it gets. So, well, in this case, I did eliminate them on forehand, so I could have this Excel lookout, and then on the left, I have the business model. So you see actually here, this part, that part is gone again. So this part actually is original model, and these basically, so these are our link constraints. So this is basically limiting the capacity each link avoids. This one was added later on. And this basically, we have all the subtours, basically making the, giving it most. Here you can also see here the actual optimal value versus the limit. And here on the bottom right, we have to switch the screen off to get rid of the allocation here. Again, we have the added basics, and we have 7 nodes, and then most should be exactly 6 active. Yeah. So here we have our full LP model. You can solve it in Excel or create an LP problem and solve it, and that's basically also what I did. Switch back to the screen. So if we then put it in LP solve, then this text you can actually copy paste it with the LP solve and run it. You can see here I did actually something slightly differently here. I didn't actually have the upper bound as a constraint, but I've actually just put them in as a bound. So actually, so here basically we have the let's say the normal node the normal node constraints. Here I have the subtour elimination, and instead here we have basically summing up the total, which has to be equal to n minus 1. And here actually what I've done is I've actually put in variable bounds, saying each variable has to have a value from 0 to 1. In this case, this is a much more effective way of actually putting it in. So this is a variable composition. You can use it in Excel, but you can use it in LP solving software. Yeah? Good. There's also another way actually to solve it. So now actually we have the subtour elimination. You can also create a subtour elimination. And in that case, actually, it's the same, but slightly different. In that case, you also have subsets. But what we do is to say that each subset should have at least one link which is active outside the subset. So if we create a subset, we should have at least one link which goes outside that subset. And that will also work. So what we have to eliminate, but we have to take a few additional steps in that case. We have to eliminate empty subsets. So a subset with no links in it will not have anything going out. Subset equal to the whole set, which we also of course have to eliminate because the whole set will not have a link going out. And also we have to make sure that we don't end up with fully enclosed nodes. So if, for example, if we take OADEC, then this is actually a subset. And then suddenly we have a link outside of that subset connecting B, but of course B is fully enclosed, so we have to eliminate that option as well. So we will only have to take the subset with B in it. So there also we have to be careful with. So this is, and it has a couple of advantages. Actually, you have fewer subsets in this case, with fewer evaluations, but you have to take more algorithmic steps actually to make sure that it's fully compliant and you don't make any errors. So it's a slightly more difficult method, but it makes it easier to solve. So in this case, you have to see OADEC and CB. So suddenly the actual outside link would suddenly be to B. In that case, T would still be not connected. So it would still not fully fulfilled. Okay, let's have a 10-minute break and then we'll talk about maximum total.